Hello everyone, welcome to this webinar. My name is Iqbal Singh Josan and I'm going to present this webinar today on wireless link engineering part 2 of 2. If you want to interact with me, you can ask me questions by typing in your question in the chat box at the bottom of the screen. So I hope everyone can hear me right now. If you have any problem, just let me know by typing in the chat box. Otherwise, we'll move forward. Okay, so this is the second part of the webinar that we started 2 weeks back. In the second part, we are going to cover these areas. We'll learn about the fading models. First of all, we'll learn about how fading works, what are the different types of fading channels, and how do they apply to the macro, micro, and femto cells that we see in the cellular communication networks. Then we'll go to the path loss models and how these propagation models are applied both for outdoor situations as well as indoor situations. And some of these models, who are in the field, you might have heard the names of these models. Egli model, Okumura model, Hatta model, COS231, and COSY model. So we'll go through each of these models, and we'll also explore the impact of foliage. Foliage means trees, the density of trees in a given area. How does it affect the RF propagation losses, and also the building penetration losses. You might be aware, like inside the building and outside the building makes a lot of difference in the strength of any wireless signal. So we'll explore that area too. And there are a few indoor propagation models which can be used for indoor areas too, for wireless LAN and femtocells applications. 1SM multi-wall model and a linear attenuation model. And finally, we'll go through, walk through some link budget analysis, where we'll incorporate these models to do our calculations for path loss and apply these to real-life applications for LTE, UMTS, or GSM as applied to macro, micro, and femtocells. Okay, so let's move on now. Now let's recall in the last, the part 1 also, we talked about this small-scale variation. This small-scale variation is on a near a handset is caused by fading effects. This is due to multipath propagation, and this is of a great interest to us because when we do our calculations for path loss, we have to study how this fading happens and what we can do about it. Okay. Now let's have a recap of from the basics of this fading. So the fading can be classified on different criteria. So you could have based on channel, like a fading channel could be called a Gaussian channel or a Rayleigh channel or a Riccian channel, or based on frequency. It could be a flat fading, or it could be a frequency selective fading, or it could be classified based on the rate of change of amplitude and phase, like it could be slow fading or fast fading. So let's learn about this in a little more detail. So if it is a Gaussian channel, so Gaussian channel is the ideal case. There we are assuming there are no other effects, no other fading effects actually. No, the only impairment in the channel is caused by the natural additive white Gaussian noise, AWGN. This is, you can't avoid this. This is there inherently in the universe. It's present, additive white Gaussian noise. If you recall from part 1, like because of the temperature, the absolute temperature of anything above 0 degree K will generate noise. That is this additive white Gaussian noise. So even if you have no fading, no reflection, no refraction, no diffraction, still you have this additive white Gaussian noise, and that represents the sense of that represents the ideal channel or a Gaussian channel. So let's move on to the next one, the Rayleigh channel. Now in Rayleigh channel is the worst case scenario. This is the most commonly encountered scenario in cellular communication networks, because you really don't have a line of sight. In a downtown area of a big metroplex, you really can't see the cell tower. The handset can't see the cell tower. You have multiple independent paths. So, so it represents a worst case. And Rayleigh is after the name of the researcher who did some research on this type of fading channel. That's why we call it a Rayleigh channel. Well, there is another one called a Riccian channel. There is something between an ideal case and a worst case scenario. Like, you know, in some situations, it depends. If you are lucky, you might be closer to a cell tower. So you may have a component of the signal that is received directly, but many other components which are coming through reflections. Reflections from the building, reflections from the hilltops, or any other objects which are big enough to reflect the signal. So, and you have to simply do a vector sum of all the signal components to arrive at the final signal strength level at the handset. So that is called a Rician channel. So this is also encountered in real life, like in a wireless LAN situation. You know, you must have noticed that the wireless LAN signal, although you are inside the building, where the signal you hardly feel any variation in signal level when you move from one place to another place within a big hall, right? So because you have a component of the signal which is dominant and which is line of sight. And you could have other components too, but usually you don't encounter the situation of fading signal. In very rare cases, you see that. So that type of channel will be called a Rician channel. Now we can characterize these three different types of channels using a value called K. So K is nothing but the power of the signal component in dominant path. What is the dominant path? The line of sight path, for example. The line of sight path is a dominant path. If there is no line of sight path, then whatever the strongest signal coming through any reflection, that will be the dominant signal. So ratio of the power in the dominant path to power in the scattered paths. So that is the value K. And you know, the value of K can be characterized for different types of channels. For Gaussian, it is infinity. Why it is infinity? Because there is no scattered path. So the denominator is 0, that makes it infinity. For a Rayleigh channel, K is 0. Why? Because in Rayleigh channel, there is no line of sight path. And that makes it 0. For a Rician channel, it could be anywhere between 0 and infinity. Now, if you look in the text on the slide, that large cells tend to be Rayleigh. Large cells means like you have 10 kilometers, 50 kilometers of that distance range. Those are large cells, or bigger than that actually, right? So they tend to have lower values of K. And small cells tend to be Rician. Small cells, as we talked before, it could be wireless LAN cells, femto cells, or pico cells, where the distance is small. You are either on a university campus, or an enterprise campus, or even in your home actually, right? So there the small cells, they tend to be Rician channels, and the value of K is anywhere between 5 and 30. It's an estimate from measurement section. Okay, so let's now move on to the next one. A classification of fading based on frequency. Now flat fading. When we say flat fading, what that means, that all frequencies in the channel are equally affected. That, you know, in any signal is even you have a single carrier frequency, still you have a band around that carrier frequency. There is a center frequency, but a band of frequencies which are used around the center frequency. So if all the components are affected to an equal extent while fading, then we call it a flat fading channel. Now, flat fading channel is very easy to handle because at the receiver you can equalize all the components of the signal to the same extent. So the receiver design will be much simpler actually if you have a flat fading. But if you have frequency selective fading, the challenges are much higher. You know, here you see, it's just an illustration here, like in the normal signal you have different frequency components which are represented here, visually represented here by different wavelengths. The waves are wider or compressed. Higher frequency, the compressed waves, and for lower frequency you have wide apart waves. So if each component of a frequency band, it fades to a different extent, then we get this frequency selective fading. Now here it's a little more challenging because if your signal content is spread out on all these frequency components, then part of the signal content, the information content in the signal will be faded. You will lose part of the content actually, right? And it will be hard to recover that. Although there are schemes to do that, but still it will present more challenges. That is because the different frequencies in the channel, they are affected to different degrees in amplitude as well as phase. It's not just the amplitude, but the phase also affected. Why the phase is affected? Because the wavelengths for different frequency components are different. So if the propagation path is delayed by the same extent, each frequency component will suffer a different fading in phase. Okay, so now the last classification is based on slow fading, which is how fast the amplitude or phase of the signal level changes. Now this is very common. If you have been listening to AM broadcasts of a radio on a shortwave frequency band, you might have noticed that the signal level keeps on changing slowly. It peaks and then it falls down. It peaks and then falls down. That is type of slow fading. A fast fading, where it could be quickly changing. Like suddenly it drops and suddenly it rises up. Now, this is of course has uses. This type of fading has its own uses. You could use time diversity for reliable communication. Like what do you do? Like if you can characterize the behavior of the signal here, like let's say every 1 microsecond or 2 microseconds, I am getting a very strong signal. And then every 3 microseconds, I get a component of signal which is very weak. And then every 4 microseconds, I'm getting a very strong signal again. So if you can characterize the behavior of this fading, you could use time diversity. You could transmit multiple copies of the signal or the multiple copies of the content in the signal, so that even if you lose one copy, you still have another copy transmitted in a different time slot. So time diversity, of course, can overcome the challenge of fast fading. Well, now let's move on to see how the different cells are classified in cellular communications. You know, basically there are two factors here. One is the cell radius. Cell radius defines how big the cell is. Okay, there is a question about time diversity. Okay. In time diversity, let me go back to the slides. In this illustration, the fast fading signal, the strength of the signal is varying with time actually, right? If your x-axis, you see, you go right on the x-axis, the signal level changes. It suddenly rises to a very high level, suddenly drops to a very low level. Now, if you could transmit multiple copies of data onto these frequency components, you can still retrieve the data. Even if you lose your data in this part of the signal, I don't know if you can see the mouse moving around. Okay, this is the faded part of the signal. If you lose data here in this part of the signal, which is faded, and if you have another copy of data transmitted in this part of the signal, you can still retrieve your information content. Although you lost one part of the signal, and the copy of the data is present in a different part of the signal too, a different frequency portion of the signal. So time diversity is time diversity. That means you send multiple copies of the signal onto different frequency components. Even if you lose one frequency component, you still have a copy of data available on a different frequency component. I'm trying to oversimplify this because when we go to OFDM, that's where we really use this actually in LTE. This time diversity is used actually. It is capable of using that. So simply time diversity means that you are sending multiple copies of your data which you are transmitting on multiple frequency components, so that even if you lose one frequency component, which might get faded as because of fast fading, you can still retrieve your data content from a different part of the signal, either from a different frequency or the same frequency transmitted in a different time slot, right? So any questions? Is that clear? Clear enough? Okay. So cell radius defines the size of the cell actually. You know, you could have large cells or you could have small cells. And in large cells you have macro cells or a small macro cell. Typical cell radius up to 30 kilometers for a macro cell, up to 3 kilometers for a small macro cell. This is like based on an industry consensus, like whatever numbers I'm giving you here. So in small cells you could have microcells, picocells, and femtocells. Microcells are really less than 1 kilometer, less than 500 meters, or less than 10 meters. So here on the rightmost column, you see how, based on the size of the cell, the position of base station antenna also changes. For a macro cell, it will be outdoor typically. You can see the cell tower when you're driving around. It's mounted above medium rooftop level. Heights of all surrounding buildings are below base station antenna height. And for a small macro cell, it's again mounted above medium rooftop level, and heights of some buildings are above base station antenna height. And for a microcell, it's again outdoor, but it's mounted below the medium rooftop level. For a picocell, it could be either indoor or outdoor, like on a campus. On a campus, it could be outdoor as well as indoor. And if it's within a big hall or at your home or at your small business, it could be indoor. In a femtocell, it could be indoor, mounted below rooftop level or ground level. So let's move on. It's just a classification of cells, different types of cells, and how the position of base station antenna changes. Now, before we move on, let's pause for a while And let's try to answer this question. So which of the following represents a dense urban cellular environment? A dense urban cellular environment like that in a downtown or a big metroplex in the center of the city. A Rayleigh channel or a frequency selective fading or a fast fading or a Rayleigh channel. Yeah, take a second and okay, yeah, someone replied, a Rayleigh channel, yeah, it's the worst type of fading. It could be frequency selective fading, yes. Very good. Okay. Okay, so 4 is the most appropriate answer. Although you could have frequency selective fading or fast fading, but we really need some data to decide that. But Rayleigh channel is definitely a very definite answer. It is definitely a Rayleigh channel environment. So now let's look at this is a table which can be used to decide, like, for a particular cell size, what type of model should I use. So as you see, for large cells and for macro cells up to 30 kilometers, we could use Egley, Okumura, Heta, or COS231 models. And for small macro cells, we could use COS231 and COS2Y. Now for small cells, the situation is different because micro cells, pico cells, femto cells, there is a separate table for that which you can use for your reference. This is gathered from the industry data, how different companies and universities have come up with some models for small and micro cells. And now we won't go through the detail of each of these entries. When you get the copy of the slides, you can use it as a reference, just as an industry reference. Okay. Now let's look at some of the propagation mechanisms that are used in macro cells. So for a macro cell, you could have a line of sight propagation where the signal power decays as the inverse square of distance, d minus 2, d exponent minus 2. Or you could have a single diffraction where now, the equation changes here. It's again a negative exponent of 0.5, but you have two distances here, the d1, distance d1 from the cell tower to the top of the building, the edge of the building, and from there it gets diffracted to the handset, and the other distance d2. And this is the behavior. This is experimentally determined behavior for a single diffraction. So in multiple diffraction, you have multiple rows of buildings, which is quite a common situation in any metroplex. There you could have multiple diffracted signals coming here, and here the behavior is d exponent minus 1.9, where d is the distance from the edge of the nearest building to the handset. And you could have a reflection too, a reflected signal traveling a distance d1 from the cell tower to the face of the building, and then traveling a distance d2 to the handset. So the behavior in this case, the signal power decays with a negative exponent again, minus 1, but sum of distance d1 plus d2. Yes, these data are related to power, signal power actually, how the signal power decays with all these different phenomena. Yeah. Then you could have a scattering also, scattering from the irregular terrain like undulating land where you have little hill and then a little going down, the line is going down and going up again. So again, the distance d1 and d2 are defined here, and there is scattering from the trees also. Scattering, we are talking about scattering here. So the behavior is a little different. It's the product of d1 and d2 with exponent of minus 1. So there are 1, 2, 3, 4, 5 different types of phenomena that happen when when we consider RF propagation in macro cells. Well, there is a question that why LOS propagation have strongest decay power. Well, that is coming from basic physics actually. In line of sight propagation, you have a single component of the signal which is traveling over a certain distance at a certain frequency, and we just get the physics of it, and that is the way it is. But in other cases, like for diffraction, actually in diffraction it's minus 0.5, but it's a combination distance d1 and d2. Here actually, if there was no diffraction, you would have no signal here. On the you are in the shadow zone here. The building is hiding the signal from you, but because of diffraction, you are receiving the signal. So instead of obstructing the path of signal, because of diffraction, you have getting the signal. So the behavior is slightly different here. So you are actually getting a diffraction gain here. Diffraction gain is happening because of the diffraction phenomena. Otherwise, it's simply obstruction. You know, there's no line of sight between the handset and the cell tower. Multiple diffraction, again, you get multiple signals. The signal gets strengthened a little, so there's a little less decay here. It's minus 1.9, slightly less. It's almost line of sight path, but because of diffraction, we are adding to the signal. That's a diffraction coming from different points on the buildings. Well, okay, there is another question. So LOS is not preferred in industry? No, that is not the case. LOS is always preferred. LOS is the simplest mode of communication and it's always preferred. It will always be a dominant path, actually, you know. But for other modes, like there are obstructions, but still you see getting signals from different sources. Sometimes you are not in line of sight, but still signal arises from somewhere and adds to the strength of it, or even subtracts from it, actually. Right? So LOS is definitely preferred in the industry. It's always good to have a line of sight path, but it's always not the case. That's the ideal case, actually. If you have LOS, it's very ideal case. I hope I answered your questions. Okay. Yeah, you know, these are experimentally determined behaviors. Yeah, some of these might appear counterintuitive, but that is the explanation for it, right? So line of sight is always the best. But yeah, when we have other phenomena, then the behavior changes, actually, you know. As I told earlier also, like it may not be the exponent minus 2. It will be different power of D. Okay, so now let's move on to the propagation mechanism in microcells. The cells are getting smaller here, so we are only concerned about reflection, line of sight propagation, and diffraction. I simplified a little. There are not too many things happening in case of microcells because the handsets are closer, in a closer range of cell tower or the base station. But the behaviors are the same. And next we come to indoor areas. Indoor areas, it's simplified a little, but you know there's more things happening here. You could have absorption, access point or a base station or a node B on the other side of the wall, and your PC or a handset is on this side of the wall. So the signal gets absorbed by a constant value C. There is absorption in the wall itself, and that depends on what type of wall is there in between the access point and your computer. You could have reflection, again the same behavior as we saw before, reflection from the wall. You could have diffraction too, from the edge of the wall. If you are in the hallway, there is a edge of the wall here, it could get diffracted. You have line of sight propagation, definitely. The most preferred one is the line of sight propagation. And then you could have a guided wave. Now this is a very special case. In a corridor or a hallway or in a tunnel, you get this phenomena of guided wave. So here the behavior is completely different. Log of E is proportional to D. Now E is the volts per meter electric field intensity. That is the way it is depicted here. Okay, so we learned how different cell sizes, the mechanisms are slightly different. And so when we have situations for each type of cell, when we are doing our link budget analysis or studying the behavior of communication in a particular cell size, we have to keep in mind all these different mechanisms. Okay. Oh yeah, the question is shifted a little, but I think it's still readable. Which of the following do not contribute to path loss in RF propagation? Just give me one answer. Let's see, what is it? Diffraction, reflection, absorption, oscillation. Yeah. So oscillation doesn't mean anything here. It's out of context anyway. Simple one to answer. Okay, let's revisit the free space loss a little. This is just a recap from the previous webinar. So we remember that this is the equation we use for free space power loss in the decibel form, where we have to input the frequency in megahertz or a distance in kilometers. And it is derived from the Fry's equation. And I hope you are all familiar with the EIRP, the equivalent isotropic radiated power. Well, then we have a log distance path loss model, which is very applicable to mobile communication environment. And this is the equation here. You know, here the path loss at a given distance D is given by, you know, this is PLDB D0, which is path loss at reference distance D0 in the far field. And N is a path loss exponent. You know, here we don't give any value, it's 2 or 3 or 4. It depends on what type of environment you are in. It's a very generalized log distance path loss model. Why it is log distance? You see it's a log of T over D0. So here for your reference, n we can use 2 for free space, and n is usually 6 in urban areas. But it's not a fixed number. You know, it could be anywhere between 2 and 6 too. Depends on what type of urban area is it. Is it a suburb or an urban, or just a wide apart urban, or what type of urban area is it? So a lot of experimental or measurement data is needed to determine that what type of index we are going to use here. X sigma is the variation. It represents the small scale signal variation in power or local clutter. So there is a adjustment for that. So for this log distance path loss model, first we need a value which is a measured value at a reference distance d0, which could be measured or even calculated actually from free space path loss. Then we add this correction here, like based on what type of area we are in, what is the value of n, take a ratio of d or d0, and apply a correction for signal variation, like within local area of a handset, what is the variation. Now this is a more of a mathematical presentation. From this basic log distance path loss model, we'll derive other models which are more practical to use as we move forward. Well, let's look at the history of this. The EGLI model was the earliest one, which came out it's named after the researcher and the scientist who published a paper on this EGLI model, and it came out in 1957. You know, at that time, you did not have any wireless towers, cellular communication towers or base stations. You only had a TV transmission or radio transmission towers, which used to transmit at VHF and UHF frequencies. So there also you have the same problem. Again, it's a radio RF propagation. So he arrived at this model based on a number of measurements in the actual transmission area, and he made some assumptions that the terrain is the terrain where he did all these measurements. It consisted of gently rolling hills with average hill heights of 50 feet. So he put those assumptions in his paper actually. And transmit receive distance is 1 to 50 kilometers, and frequency range he considered was 30 megahertz to 1 gigahertz. Now, you know, although this model was derived from TV transmissions, but it is also applicable to cellular communications. We can apply it. So this provides us a very good guidance to how to develop our models for cellular communications. Now let's look at a little more detail. Now, you know, this model gives us a median path loss over irregular terrain. As we said in the previous slide, when we have irregular terrain, it applies to only that situation. It doesn't consider the absorption by trees or diffraction or reflection. It's just you have irregular terrain and what will be my path loss. So here L50 is the 50th percentile of total path loss. What that means that if you make a number of measurements in the area, then and arrive at a value L50, then 50% of your measurements are below this value and 50% are above this value. It's the 50th percentile total path loss. So this model, this equation gives us the L50 value. We derive this from gain of base station antenna, gain of mobile station antenna, height of base station antenna, height of mobile station antenna, and you know there is a factor here called beta. It depends on frequency. He determined this factor empirically. So we can just use this factor to arrive at an estimate of our median path loss. L50 is the 50th percentile or median path loss. So equation looks very simple, you know, but it only considers the irregular terrain, doesn't consider any other factors. So we need more than this for actual application to our mobile communication environment. Although for a very rough estimate, it's very good. Like if you're starting out and setting up your macro cells in some greenfield area where nothing is there before, this could be a good model to start with. It gives you a good estimate of like, okay, this will be my estimated path loss in this region. And then you can refine your model after that using more advanced models. Now, although you know the equation we saw before, it gave us L50 in dB, but EGLI also provided us a lot of curves. From those curves, we can derive a terrain factor. That helps us to calculate any percentile, like a 10th percentile or a 20th percentile or a 60th or 80th or 99th. For reference, I have given some values here which are taken from the EGLI curves which are published in the literature, and for each frequency. So now, for example, if you are trying to calculate for 1 gigahertz, okay, there is a question. So we will add diffraction and another factor EGLI model to get advanced cellular model. Well, yes, it's that, but then we don't we don't call it AGLI model. We develop different models. So this is providing a basis for that. This is providing a basis for other models. So be patient for a little while, and we'll come to the actual models that we are going to use. But this is the beginning point. We derive our inspiration and our understanding from AGLI model. We understand how AGLI model works, okay, and then move on to the other models like COST231 or COST-Y or Hatha model, and more refined models, how we can use them to do our actual calculations. But here, for a very high level calculation, we can still use AGLI model. So using the terrain factor table, we could do some calculation here. If the frequency is 1 gigahertz and we want to calculate the 99th percentile, okay, then we just subtract 29. Now, where this 29 come from? Actually, it should not be L90 dB, it should be L99 dB. Yeah, so here in this table you see for 99th percentile for 1 gigahertz the terrain factor is minus 29 dB. So we make a correction. If we want to calculate our 99th percentile, we subtract 29 from the L50 dB. So it's also a very practical model, can be applied to many situations and has been applied in the past. Now let's move on to the more well-known Okumura model. Okumura was a Japanese scientist who was the pioneer in applying these RF propagation models to wireless communication systems. So he applied this to large cells based on measurements in Tokyo in 1960. Transmit receive distance is up to 100 kilometers. Frequency range is, this is the frequency range, 150 megahertz to 1920 megahertz. And you could extrapolate up to 3000 megahertz too. Base station antenna height up to 200 meters. So you know, when you apply a model, you have to know what are its boundary conditions, or what are the restrictions on it, so that you can apply it correctly, so that your estimate is as close to the real value as possible. Well, other things about Okumura model. So the correction factor is based on terrain categories. So he categorized the terrain into 3 types: urban area, which is the baseline, that means heavily built areas, tall buildings and apartments, or you could have suburbs, residential houses with 1 to 2 story houses, with of course some obstacles near the mobile set but not very congested. That means there are still some open spaces between the houses. And open area. Open area is open fields, farms, not tall trees or buildings. So the correction factor changes based on what type of area you are considering your macro cell. Well, there are other correction factors. Terrain undulation height. That means what is the change in the height of terrain actually? The average change in the height of terrain. Average slope of terrain. Isolated ridge height. Mixed land sea path parameters. So you know, he tried to go into much more detail here. Compared to AGLI model, which only consider terrain factor, now you are classifying the type of terrain and even height of what is the average height of the peaks and the lows in the terrain, and so on. So this has a little more practical uses. Now this is the final equation that we come out with Okumura model. Again, you get the 50th percentile. You have a free space path loss L free, which you calculate from the free space path loss equation, and then you have other correction factors here. Median attenuation relative to free space loss in urban area with base station height this and mobile antenna height. These are the boundary conditions here. Function of frequency f and distance t. Well, again, the G area is the correction factor due to terrain, urban area, suburban area, and open area. Now these boxes are just for reference. Whenever you really want to do some calculation, you just directly use this equation, look at what correction factors are there, input those values, and arrive at your L50 dB. Well, there are some more explanations here. Corrections to antenna gain factors if base and mobile antenna heights are different than 200 meters and 3 meters. So again, some values you can use here. Now let's go to Hatha model. This has more practical uses. Now Okumura model is good, but it's difficult to apply in the real world. So Hatha model is a simplified version of Okumura model, which is applied to large cells, and it's really applied actually. So many RF planning softwares use Hatha model actually. You know, when you go work for for a company as a RF optimization engineer or something, they will already have some software running over there, right? Those software are using one of these models actually, and behind the scenes. Either you could do your manual calculations, or to speed up, you could have a software doing this for you. So here again, the restrictions are there. Transmit receive distance is more than 1 kilometers, frequency range up to 1500 megahertz only, base station antenna height up to 200 meters, and mobile height is up to 10 meters. Now this is the equation that comes out of the Haza model. So you have the center frequency, range, the distance, the base station height, mobile height, and then some correction factors. So here you see for small and medium cities, for large cities, and for large cities more than 300 megahertz, you have different correction factors here which need to be calculated. So here I am only showing you the results. These are mathematical results which are of practical use in our real situations. Now this is the equation for suburban areas, and this is the equation for open areas, the lower one. So you have three different equations for urban, suburban, and open areas. That's what we get here. So sounds similar to Okumura model, but it's much more simplified. Much more simplified equations that just need inputs of, like in this case for open areas, you just need the carrier frequency, and that's it. And you need the L50 dB value for urban. Now next comes the COS 231 model, which also has a very good practical application. But how it's different from Haza model? Well, it's again based on Okumura model, but they modify the results to come out with the frequency range up to 2000 megahertz. It's 1500 to 2000 megahertz. Base station antenna height and mobile height is about the same. Well, and this is the final equation that we get. Again, we have classification of this correction factor for small and medium cities and for large cities. So I'm going to quickly pass through these slides because this is more of a mathematics and just introduction, and move on to the actual examples, and we'll see how we do the analysis. Okay, before we do that, let's pause for a while and try to answer this question. So which of the following do not contribute to outdoor propagation models? Take a second. And so wavelength, absorption of RF waves by human body, base station height, ambient light in the propagation medium, distance between transmitter and receiver, atmospheric temperature and pressure, mobile station height. So which ones do not contribute? Number 4, many of you answered number 4, yeah, that is correct. Also the atmospheric temperature and pressure also do not. Yeah. 6 is also true. Atmospheric, if you look at the recall the equations in the models, we never have this. We never have to enter the atmospheric temperature and pressure over there, right? And also absorption of RF waves by human body, we don't consider that. Although you might think it's counterintuitive, like human bodies we have said they absorb RF propagation, but we never consider here the presence of people, that how many people are present in the room, because that is it's not a very useful factor. Okay, there is a question here. SAR. What is SAR? Can you please expand on that? Okay. Okay, fine. We can talk about this specific absorption rate. Okay, yeah. That is a factor, but our models do not consider that. Our models have the values that we enter in our models. We don't directly enter specific absorption rate. We only have other things going on, other phenomena going on, right? Of course, that is a specific absorption rate is there. There is a specific attenuation rate that is very similar, but that is the one we'll be using in some of the models as we go on. Okay. So COS Y model. Now here, this is again another refined form of COS 231 model. This is applied to large cells. Now here, we go into much more detail. We even consider the heights of buildings, widths of roads, building separation, road orientation with respect to direct radio path. It's too much detail. But if we want to refine our models, we have to do that. Transmit receive distance up to 5 kilometers, frequency range up to 2000 megahertz, base station height is 50 meters only, and mobile height is 3 meters. So COS Y model Okay, this illustration explains how we use different parameters here. We have heights of buildings, H roof, widths of roads, W, building separation, B, and road orientation with respect to direct path. You know, a mobile user, he will have the radio signal coming from the cell tower at a certain angle. So that angle is also considered in this model. So much more detail here, much more refined. That's what will make it more of practical use. So a cost Y model takes two cases. The first one is the line of sight case, which is based on measurements in Stockholm. And this is the equation here. You know, looks very simplified here. It's because it's line of sight. You know, just need the distance and the frequency. That's it. For a near line of sight case, there are more corrections here. You have L0, which is the free space loss. Then you have rooftop to street diffraction loss, LRTS, and multiple screen diffraction loss. You know, now we are focusing on a smaller cell size, a picocell or maybe a femtocell, right? Because picocell can use cost Y model. So where the cell sizes are much smaller, so these parameters will become very significant. What is the height of the building? What is the height of the roof? What is the separation between the buildings? What is the width of the road? What is the street orientation for mobile users? So that's why all these parameters are coming up. A lot of diffraction is happening here. Rooftop to street diffraction or multiple screen diffraction loss. So those are defined here. Okay, so there's a question here. LMST, what is screen? Multiple screen here means multiple wall actually. You know, instead of using the word wall, they have in the literature they use the word screen to generalize it actually. Screen could be any tall structure which looks like a wall. So multiple screen diffraction loss. So for near line of sight case, now this is a near line of sight case, right? Like you don't have a direct line of sight, but there is some obstruction in between, which is diffracting the signal. So near line of sight case. This is the equation here, and you have the rooftop to street diffraction loss also defined here, LRTS, where you enter the street width and the frequency or the orientation loss. Orientation loss is further defined here in another equation. You know, here even the equation changes for the angle, the range of the angle, the street orientation, for 0 to 35 degrees, for 35 degrees to 55 degrees, or for 55 degrees to 90 degrees. Well, so this is your multiple screen diffraction loss, or multiple wall direction loss, or multiple building direction loss. So here you enter the parameter B, which is the separation between the buildings. You have the frequency and you have other factors here, Ka, Kd, and Kf, which are defined in other slides. This is Ka. You can calculate the values of Ka from here. You have Kd over here. This is for, when you get the slides, you can work on these whenever you are encountering a situation where you need to calculate a link budget for, let's say, a picocell. We'll give one example here. We'll walk through one example here. Does all that. Now here, this is a little, you know, if you don't want to go through all those detailed equations, there are some default values which can be used. The roof height is 3 plus roof height, 3 into number of floors plus roof height is the average. It's a default value you can use. Although you can refine your model by changing these values. Roof height is 3 meter for pitched and roof height for 0 meter flat. So pitched is like you have a pitch like this on top of the building. So it depends on, in some countries you don't find this type of roof, you only have a flat roof. But in some other countries you have a pitched roof. So based on that also the, you know, the roof height will change. Building separation, these are only some estimated values. It could be changed from location to location. Width, street width also might change. But these are the default values which can be used to get an estimate. Now foliage loss. So you know the trees also absorb RF signal power. Now this is a model which is recommended by ITU for out of leaf case and for in leaf case. Out of leaf means when you have a fall season, when the trees don't have leaves on them. And in leaf is when you have spring season or summer. So even the presence of or absence of leaves on the trees also affects the absorption, how much absorption happens. And this has been measured and found to be fit into this empirical model, where you just input the frequency and the depth of trees. E is basically the height of trees, dt. Well, now we're coming to the building penetration loss. The building penetration loss, there could be losses through a wall. When the signal passes through a wall, there could be a wall loss. There could be a room loss. Or once the signal enters the room, it suffers diffraction, reflection inside the room too. And room loss is nothing but the median loss from measurements in the whole room at 1 to 2 meters above floor. So 1 to 2 meter is the estimated height of the mobile handset or a computer, which could be present in the room. So that is called a room loss. Or you could have a floor loss. In case of a floor loss, you don't consider just one room, but all the rooms on the same floor. So median loss in all the rooms on the same floor is called the floor loss. Then building loss. We just consider all the floors in the building and all the rooms in the building, and just measure what is the median loss in all rooms on all floors in the building. That is the building loss. So when you are designing a wireless LAN network, or if you're designing, or you're just trying to analyze how the signal is received inside the building, so all these losses have to be considered. So for line of sight conditions, the total path loss is given by this equation, which could be used. The inputs are frequency, the distance, S is the distance between external antenna and the wall, D is the distance, like lowercase d is the distance between external wall and the mobile antenna, uppercase D is the perpendicular distance between external antenna and the wall plane, and theta is the grazing angle, the angle at which the signal is incident on the outside wall, the external wall. So this is how we model the situation here for building penetration loss. Now total path loss is given by this equation. Even we consider the number of penetrated internal walls, P, parameter P here. And then we have a alpha. Like earlier somebody was asking about specific absorption rate, but here it's not absorption, it's the attenuation rate that we are considering here. dBs per meter is the rate of loss when there are no internal walls. That's how fast the signal attenuates actually, right? Okay. So then we have line of sight conditions, total path loss. Here again we describing more parameters. Wi is the loss in internal walls, We is the loss in external wall when angle is 90 degrees, Wge is the loss in external wall when grazing angle is 0. So it's mostly mathematics here, but we're just going through it. Now here again you have some default values which could be used. If you want to simplify your effort, you could just use some recommended default values, and your calculation will be fairly accurate in that case. So these are the values. Even for the type of this wall, the We is 4 dB, Wi is 4 to 10 dB, and Wi is 7 dB for concrete walls, and is 4 dB for wood and plaster. So really you have to work with the civil engineers or the facility engineers in a building when you're designing a wireless network. You want to know what type of building material is used, how many floors are there, how many rooms are there, and from these models you could get a very reliable estimate. Okay, there is a question here. Where to use grazing angle in this equation? Yeah, this equation is a line of sight. There is no grazing angle here. This is total path loss. We don't need grazing angle here. So near line of sight conditions, external antenna is above the building height, right? The first case is external antenna above building height. So there's some diffraction happening here. This is the situation illustrated here in the picture. You have different floors, and you have to know if there's a basement or not in that building. And the second situation when external antenna is below the building height. Here you see there are two ways the signal can reach the other side of the street. One is Oh, there's a question here. You're talking about previous slides. Okay, let me see. Okay, so here you're asking about the grazing angle, right? That's your question? Yeah, here we don't see that this is near line of sight. This is the equation. So this is near line of sight condition, right? Is this you're talking about this slide? Yeah. So here we don't need a grazing angle. This is a near line of sight condition. Okay, previous slide. Oh, yeah, I'm moving forward. Sorry for that. Near line of sight condition. Yeah, here also we don't have the grazing angle. But we have this factor WE and WGE. If you see at the top, WE is the loss in external wall when grazing angle is 90 degrees, and WGE is the loss in external wall when grazing angle is 0 degree. So this is how it factors in. Is that okay? Is this the slide we are talking about? So grazing angle does have impact here on WE and WGE. So we don't put the WE. How to find the angle? Okay. So you're saying how to find the angle. So this is from the layout of your cell actually. You have to get a layout of the place where you have to see what is the building layout, or what is the plan of the area over there, and where is the cell tower. And you can just from simple geometry you can draw that how the signal will reach the external wall of the building, and just estimate an angle over there. If you don't have access to this type of plan, then just assume 90 degrees. That's it. Just assume 90 degrees. That the cell tower is transmitting a signal at 90 degrees to the external wall. Okay. Okay. Very good. So let's move on. I have to skip some slides. We covered this. I think we need to do this question. Okay. So let's pause for a while and try to answer this question. The dominant causes of faded cellular signal inside a building are trees near the building, external and internal walls, stronger wireless LAN signal, floors, furniture density. So what do you think causes a signal level to fade inside a building? Yes. Yes, number 2 is correct. Number 4 is correct, floors. Number 5 is also correct, The more furniture in a floor, the more there will be absorption actually, Trees near the building, yeah, trees are outside the building. So those do not have any direct impact. Once the signal enters the building, you have all these other factors. Okay. And of course, stronger wireless LAN signal does not have any impact. It doesn't have to do with the stronger wireless LAN signal, because those will be on different frequencies. All right. So let's consider some of these indoor propagation models. The first one is the one slope model, which is a very simplified model. In fact, you need nothing here but a decay index n and the distance. That's it. Once you know the L0 dB is the path loss at 1 meter distance. It's very simple to apply, but then it's not very fine also. But it just helps to understand, okay, if we know from measurements in a specific room situation that this is our decay index, we can easily calculate, have a high level estimate of our path loss. Well, this is the one which is very common, a multi-wall model. In a multi-wall situation, you have multiple walls on a floor, and this is the equation you want to use. You will need a free space loss. Of course, the free space loss is a very standard equation between transmitter and receiver. But then you have correction factors. So LC here you can ignore. It's coming out of some mathematical linear regression, and you can take it 0. It's very negligible. But other factors you have to enter. You have the number of penetrated walls of type I. Now, there can be different types of wall. There could be concrete wall, or a wall made of wood, or simply a partition. KF is the number of penetrated floors. You have a loss of wall type I, and its loss between adjacent floors. There is a empirical parameter. So we have a table a few slides from now where we can use some values, some suggested values of this value B and the number of wall types. Okay. So this model defines two types of walls, light wall and a heavy wall. And this is the definition here. It considers any wall which is less than 10 centimeter made of plasterboard or particle board or a light concrete wall is LW1, and heavy wall, which is a load bearing wall, walls can be of two types, load bearing and non-load bearing. It seems like we are discussing a lot of civil engineering here, but that is how it is. You may have to interact when you are actually doing this type of work in the field. You may have to interact with the facilities engineer, civil engineer to understand the structure first, and then extrapolate your findings into these models and calculate your path loss. Then we have the linear attenuation model, which is another very simplified model. But you need to know the attenuation parameter here, the dBs per meter. What is the rate of loss when there are no internal walls? It's a very wide or a very, very big hall, a conference hall or something like that, right, where this can be applied. But you need to know the value of alpha here, a dB per meter, decibels per meter. What is the decay of signal power for a unit distance, where D is the distance between transmitter and receiver, of course, and then you have the free space loss between transmitter and receiver. Well, so this is the table which enumerates some values which can be used when you are doing actual calculations for each of these models, indoor propagation models, and this is at 1800 megahertz. Of course, yeah, your frequency may not be exactly same, but if it is different, then yeah, these constants may not apply directly, but still you can use these values to get some estimate of what will be the path loss. So all these different types of environments are listed here: a dense environment, an open environment, a large, or a corridor, and value of these constants are given, which could be used. So one way is that you just use these values which are provided by other researchers, like who did some actual measurements, or do your own measurements. If you are not happy with the way it's turning out, you may need to do your own measurements, have a field strength meter, and measure the field values in different locations in the indoor area, and to try to determine what will be my path loss and what should be the power of my transmitter, how sensitive my receiver will be. Or you can use these values from this table, right? Now, okay, let's pause for a while for this question. Try to answer this. Which cells will you recommend to improve indoor user experience in a dense urban area? Macro cells, micro cells, femtocells, or picocells? Just take a second and type your answer. Yes, so femto and pico both. That is the right answer. For indoor user experience, you have to use these two types of cell structures, femtocells and picocells. Now let's go to the some real examples. Let's take the example of this LTE macro cell. So LTE is the 4G wireless broadband technology that is currently being deployed in many countries. We consider here the band number 17, where the uplink frequency you can see here between 704 to 716 megahertz. Downlink frequency is 734 to 746 megahertz. So cell radius we are considering here 8 kilometers. It's a macro cell. It's a bigger cell. Base station antenna height is 100 meters. Mobile antenna height is 1.5 meters, and area is urban. So for this scenario, and in this picture you see, you have a E node B at the cell tower, and the UE, the user equipment, is a handset that the person is going to use. Now we use the Hata model here for downlink budget. We just use the equation that we had seen before, and just input our values. We take the center frequency for the downlink and do the calculation, and our L50 dB comes out to be 118.16 decibels. We plot this on this chart, the bar chart, which we have seen before, and you see here the transmitter power is 46 dBm. This is in dBm. Now on this table here on the right, you see that 46 dBm is equivalent to 40 watts. It's a 40 watts transmitter here. Then go through these calculations for the path loss. You have the losses on the transmitter that drops it down to 44 dB, and the gain on the antenna pushes up to 62 dB. Then you have the path loss here. The path loss is 118 dB, which it brings it down to minus 56 dB. And then you have receiver gain is 0 dB and receiver loss is again 0 dB. And the final, your received power level at the handset is minus 56 dB. we assume the distance between the transmitter and the receiver, between the E node B and the UE is 8 kilometers here. So at a distance of 8 kilometers in an urban environment, we use Hatta model to calculate the signal power set. It's minus 56 dB. Now, we have these assumptions here. The noise floor we typically will be minus 97 dB. It may vary from handset to handset, of course, but this is one of the typical values. We assume the sensitivity to be minus 88, and with that, we have a link margin of how much? 32 dB. So we have enough link margin to accommodate any fading effects here. Now, next we have the uplink budget. For uplink, we use the same equation again, but now we use the center frequency is different now. It's 710 megahertz. And the path loss comes out to be almost same, 117.94, which is again 118. So path loss is same for uplink and downlink in this situation. Because frequencies are not different, it's the same scenario. However, the situation here looks different. Why? Because the handsets and the E node B, the transmitters do not have the same type of power. For a handset, the transmitter is transmitting only 200 milliwatts of power, which is equal to 23 dBm, which is very low compared to the transmitter power we had for E node B. So that is why the calculations are a little different here, because handsets and E node Bs, they have different levels of transmitter power. So we start with 23 dBm, and then because of loss is only 0 dB here, so it stays at 23 dBm. With gain is again 0 dB for the handset, 23 dBm. Path loss is 118. It drops down to how much? Minus 95 dBm. So the signal is very weak here. The E node B has to be very sensitive to be able to receive the signal from the handset. That is why our noise floor is much lower here. It's a higher negative number, but noise floor is much lower. Has to be much lower for the E node B, and the receiver in the E node B has to be very sensitive too, so that we have enough link margin between the received signal power level at the E node B and the sensitivity of the receiver. Okay. Now let's go to UMTS, different technology, a 3G wireless technology, which is also deployed in many countries. Again, it's a macro cell. We assume a CDMA, FTD frequency division duplexing band 2. Uplink frequency is given here. It's 1910 megahertz, 1850 to 1910 megahertz. Downlink is 1930 to 1990 megahertz. Cell radius is again 8 kilometers, and we have the height of 150 meters for the base station antenna, and the mobile antenna is 1.5 meters. So with these values, let's see what happens. Now, just note that frequency is much higher in this case. We assume for this scenario a higher frequency band. So here you see here we are now applying COS 231 model. Why? Because Hatta model cannot work at this high frequency, 1960 megahertz. If you refer back to the slides we have seen before, Hatta model has an upper frequency range of like 1500 megahertz or so. So here we have preferred to use COS 231 model, right? Our path loss, median path loss comes out to be 158.52 dB. Now again we work out this chart. Transmitter power on the E node B, we assume again 40 watts, which is equivalent to 46 dBm. And going through all these calculations, we see that the received signal power level at the handset is minus 97 dB. Now the link margin is only 6 dB here, with our receiver sensitivity minus 103 and minus 102. So our link margin is only 6 dB. We have to be aware of that. Now in this situation, when the link margin is lower, what we can do? There are several situations several solutions we could use. So one is a very simple one: reduce the range of the cell. Like from our calculation, we find that for 8 kilometers distance, our signal level is very weak actually, and no handset can deliver a reliable quality of service. So then we say, okay, it's not 8 kilometers, it's 6 kilometers or 5 kilometers, and we'll have another cell after 5 kilometers. How RF planning works. We have to calculate that at the edge of the cell, what will be the received signal power, so that we can define our boundaries for the cell. Now 8 kilometers is okay, it's 8 kilometers, but if our signal level is not right, then we may have to either reduce the cell level, or if we have plenty of signal, we may add to the range of the cell, right? It may be more of a business decision at that point, that how much investment we can do in putting up cell towers, how many more cells we can deploy, and what will be revenue from the users. So this is here we may have to make some adjustments. Now other solution will be that we increase the power of the node B from 40 watts, we move it to 60 watts, let's say, or 80 watts, and then do the calculation again and see, do we get a better link margin or not? Now if not, then of course it may not be cost effective, it may not be practical, it may not be possible technologically or whatever, right? But that is how we do the analysis. Or we make our handsets very sensitive. Here the sensitivity is -103. Let's make them more sensitive. Let's see that the sensitivity is reduced to -110 or something like that. But that will add to the cost of the handset. Maybe the electronics is much more expensive if we have more sensitivity, because you know, as we see in a later webinar, that it's again a cost performance trade-off, both for the handset as well as for the eNode B. We have to balance out all these different competing factors with the objective of providing a good quality of service to the users. Well, okay, let's have a different scenario for uplink budget. Uplink budget, again, you know, well, there is a question here. So just curious to clear my doubt, UMTS uses only macro cell or macro and femto both? Well, the answer is it uses both macro and femto. You do have femto cells on UMTS too. In fact, there are many carriers within US which are providing that. Sprint is one of them, and many other carriers also provide that. And around the world, in Europe also, there are many carriers providing femto cells on UMTS. Sprint is, I'm sorry, I take that. Sprint is not UMTS. Sprint is CDMA. They have their femto cells on CDMA. Well, yeah, but UMTS uses all types of cells. That's the right answer. Okay, so you say, okay, so there will be same model for femto cell? No, the femto cell will have slightly different equations. We will see that, because that is more of indoor propagation, you know. For femto cell, it's indoor propagation. We have to consider the indoor propagation models for any technology, UMTS or LTE. Yeah, so we'll go through one example for that. Okay, so here the path loss comes out to be 158 dB. Well, let's work out the calculations here. So you know, again, the handset is capable of transmitting only 2 watts, which is equivalent to 33 dBm, and the received signal level in this case comes out to -109, which is the same as the receiver sensitivity on the eNode B, -109. So no link margin in this case. You know, this is extreme case, because handset signal is so weak that there is no link margin left. So really, we have to do something here. Otherwise, our quality of service will be very poor. We could follow one of those approaches, either reduce the cell size, or increase the transmitter power, or make the handset more sensitive to weak signals, and so on, and then see what is the most economical and cost-effective solution. Okay, now for the GSM macro cell, now we have a little lower frequency range for uplink and downlink. This is band 900, channel 1 to 124, and let's see what happens here. Here we are back to our HATA model. We can use HATA model here. We got a median path loss of 119.48 dB. Work out the calculations in this chart. So here we have a BTS here, base station transmitter system. So GSM is, of course, has the most deployment at this point in all the countries. Gradually, many areas are moving to 3G and even 4G now, but still we have a lot of GSM deployment. So here we see link margin comes out to be about 31 dB in our case, in our example, which is pretty much a good margin to have. And if we calculate the uplink budget, comes out to be 119.22 dB using HATA model for uplink budget, and do the calculations again. Again, our link margin comes out to be 26 dB, which is again pretty good margin. Well, again, this is subjective. I'm saying pretty good margin because I'm thinking that way. Well, but actually, we have to do actual drive-through tests in the field to find out what will be the user the user signal level, whether user going to be happy with the service or not, what we need to do to make it conform to the user requirements actually, right? Anyway, any carrier who is selling that service, they are getting money from that, and they have to provide the level of service that they have committed to their subscribers. Okay, now we come to the microcell for LTE, where the frequency range is for, now here we consider a different frequency band, which is TDD, time division duplexing. This is the one which is the most recently is being deployed. Why? Because you have the same frequency range for both uplink as well as downlink. Because you know frequency spectrum is getting scarce. The carriers have to spend a lot of money to just get a license to use a frequency spectrum. So this is a more cost-saving way of doing it. We, instead of FDD LTE, we use TDD LTE, where we use the same frequency range both for uplink and downlink. Cell radius is 1 kilometer because this is a micro cell. Area is urban. Case is near line of sight. You know, near line of sight. That means a lot of diffraction will be happening here. Base station antenna height is given here. So we also consider a street width. We use some of the default values. Roof height is 10 meters. Building separation 30 meters. Street orientation close to 90 degrees. So when we do the calculations using cost Y model, you know, we consider cost Y model, which goes into details of the street width and building height and all those stuff. Now here the calculation is a little lengthy here, but we finally arrive at a number of 131.94 dB. This is the path loss we come to. And okay, there is a question here. E node B has specific name or just to denote tower? Yeah, it's just the terminology used by LTE, by 3GPP. E is for enhanced node B. You know, there is some history to it. In case of 3G technologies, the equipment is called node B, but here we have enhanced it. It's called E node B. So this houses the BTS as well as the BSC, the base station transceiver system as well as the base station controller. Both are in the same box actually. So instead of having multiple boxes, in one box we have both functionality. So E node B. So you know, in a LTE cell tower deployment, you just need an antenna and a E node B. That's it. E node B is a box which houses the functionality of BTS as well as BSC, and then you have an antenna. Antenna is up in the building somewhere, and then you connect to an optical fiber cable to the antenna. And the antenna amplifiers are located near the antenna. So E node B is an industry standard terminology used by 3GPP to describe that box. So here we come to a link margin of 18 dB doing all those calculations, which is, yeah, looks okay, but you could improve on it as we discussed before by using different techniques. So for uplink budget in LTE microcell, it's the same frequency, so same path loss here, right? So we come to a link margin of 16 dB, again within our range. We are well above the sensitivity level and we have a link margin. Okay. Now coming to the femtocell. So femtocell, as we described, is a more indoor situation where you deploy E node B. It looks like just like a wireless LAN access point inside the building, and then we see how the RF propagation behaves inside the building. Now this is a situation where there is a single floor having different rooms. E node B is in the center room, and then you have user equipments which could be consisting of a mix of personal computers and smartphones on the sides. So here we consider the example of using the LTE band number 33. Yes, again a TDD. Cell radius is only 10 meters here. Area is indoor, multi-wall, single floor. Wall type is light, and number of walls which we are penetrating here is 2. We are assuming that. Environment is dense. You see furniture all around. And that is a typical office environment, full of furniture and people, of course. So here we use the multi-wall model, which is the best fit model for this situation, and we arrive at a path loss of 84.87 dB. This is how we work out the bar chart here. So you see the link margin is very good. It's the best possible link margin here, 39 dB. You know, because we are within a very close range of the E node B. Path loss is also less here, 85 dB. So it's a very good situation here. So that is why the femto cells are coming out as a very good solution to loss of signal inside the building. That means
setting up E nodes Bs inside the building itself. You know, otherwise in a macro cell or even in a micro cell, your E node B might be outside somewhere, right? I mean, E node B could be housed in a building, but the antenna on the E node B might be outside the building, right? But in this case, both the antenna and the E node B, the box, are in one single box. It just looks like a wireless LAN router, and you could put it anywhere inside the building. And because of that, you have lower path loss, you have more link margin ultimately, much better signal level, and your handset will have no fading effects, almost no fading effects. So femtocells is the next wave of which is happening now in telecom. This is primary objective is to improve the reception of signal inside the building, and that is how it is happening. We bring the node B and antenna inside the building. Okay, there's another question here. In any particular band, are there fixed number of users associated in that in TDD? That is 8. Well, this is a question. Well, yeah, of course there will be a fixed number of users because every user will be using some resource in the frequency. In TDD, what's the number of time slots, right? And when the number of time slots are filled up, then of course you cannot accommodate too many users in that. Now this question will be best answered in our webinars on wireless access technologies, where we'll consider all these factors here. So this is currently out of scope of this particular webinar, but of course your question is right. Yes, of course there will be a limit to. Well, no, 29th June webinar is for something else. That is for the receiver engineering. So on LTE there is no currently webinar available. Those are in-person courses. The webinar is under development. Whenever it becomes available, you will be notified on that. But your question is right. That there will be a limit to the number of users associated in any different band actually. So that's why when your user you reach a user limit, then you have to change to a different cell or install a different channel or use a different channel on the frequency band actually, right? So this we are I'm using 1900 to 1920 megahertz, or use a different channel or 20 megahertz, or use a different frequency also. So there will be so many considerations to be done over there in that case. How to accommodate more users, or how to add capacity to the network actually, right? Your answer is about your question is about the capacity in the network, like in TDD, how many users we can accommodate. Okay. Well, now we have a downlink budget here, which is again pretty good. Link margin is 39 dB. Uplink budget, link margin is 60 dB here. Not bad. In fact, very good. You can achieve very high data rates with this type of signal level and the link margin. So femtocells are the solution actually. Now we are reaching the end of this webinar. This is a list of samples and books that you can refer. Before we end the webinar, you have any more questions? Anybody? Okay. So again, how do you claim your professional development hour and certificate of completion? Okay, you are talking about COS 207. Okay, we are not covering that model here. You can maybe, you have heard about it. Yeah, there are more models. COS 207 is also there, but you can do your own research online. You find from ITU website or 3GPP website, you will definitely find information on that. I did not cover that one. I only covered the most commonly used models in the industry. But definitely there is always a copy of this. Yeah, all of you will get an email that will provide you a link to download the slides and do other things. That will happen, definitely. You will get a copy of the slides, because you do need the slides for your reference actually, right? There are a lot of mathematical equations here that you have to use to do your estimation. So again, after this webinar ends, you will be directed to a forum page at this link, where you give your feedback and respond to a problem statement from this webinar. So you must respond to the problem statement in order to claim your certificate of completion and provide an answer to the problem. And if you have any other questions, you have my email ID and a link on the LinkedIn profile, and you can Twitter me also, or visit our website or anything else we can help you with. Okay, so we'll end this webinar, and there is a question. Somebody, you have not received previous certificate. Oh, I think there must be you have to, as I said, you have to provide answer to the question in the comment box, right? So once you provide the answer to the question that is asked, definitely the certificate will be mailed to you. Okay. So other is kindly notify me when the webinar on wireless technologies will be available. Yeah, all of you guys are on my mailing list. As soon as any webinar becomes available, you will be notified. You will be invited. Yeah. Any other questions, please? Okay. So I'm going to close this meeting and just wait for a window to pop up on your screen that will direct you to the certificate of completion page, and you can take over from there.